Okay, let me begin. What we're studying now is sampling theory. That's finding the distribution of sample statistics. This will describe how a statistic behaves. We'll be using it later on to assess the accuracy of that statistic. If it's used for estimation, it's used for other reasons as well. When the subjects in a sample are chosen at random from a population, observations made on them will be a random variable. When you compute statistics from those observations, that'll also be a random variable. We want to find the distribution of those statistics. We'll use that later on. The distribution of the sample mean. Suppose you've taken n observations from a normal distribution, mean mu, standard deviation sigma. Both mu and sigma will be unknown. We want to find the sampling distribution of x bar, the average of those n observations. It has a normal distribution centered at mu. So that means the value of x bar will be varying about, it could be above mu, it could be below mu. On the average, it'll be equal to mu. Its standard deviation is sigma over the square root of n. Notice that the standard deviation of x bar, the standard deviation of the normal distribution from which x bar is coming, decreases with the value of n. So the larger the sample size, the more concentrated the distribution of x bar will be around mu. The central limit theorem says that even if the data is not normally distributed, the individual observations are not normally distributed, x bar will still have approximately a normal distribution when the sample size is large, rough rule of thumb greater than 30, with mean mu standard deviation sigma over square root of n. The distribution of sample proportions. P is the proportion in a population. It's the probability of success of, you can regard the population divided into two groups. A group of interest, the proportion in that group is P. So when you take a sample of n from the population, whether an individual case belongs to that group or not, the probability will be P. P hat is the sample proportion. It's the number of successes, the number of cases that are in that group over the total number of cases. This statistic has a normal distribution with mean equal to P. That means that P hat, the sample proportion, will be varying about P, and sigma P hat tells you how it's varying about P. Sigma P hat is square root P1 minus P over n. So again, notice that n is in the denominator, and if you take n bigger and bigger, you make sigma P hat smaller, and the distribution of P hat will be more concentrated around the value P. The distribution of differences. Quite often when you have more than one population, you'll have a statistic from one of the populations, say a mean or a proportion, statistic from the other population, and to compare the populations, you'll probably use a difference. The sampling distribution of a difference in two sample means. Here we'll use this property that if you have two random variables, each having a normal distribution, then their difference will also be normal. The mean will be equal to the difference in the two means, the mean of x minus the mean of y. The standard deviation is the square root of sigma x squared plus sigma y squared. So we have two normal populations. mu1 and sigma 1 are the mean and standard deviation for population 1. mu2 and sigma 2 are the mean and standard deviation for population 2. We have n observations from population 1 and M observations from population 2. Quite often, N and M are the same values. The objective is to compare the two population means. X bar comes from a normal distribution. Mu X bar equals mu1. Sigma X bar is sigma 1 over root N. Y bar is normal with a mean mu X bar equal to mu2. Sigma X bar equal to sigma 2 over root N. Now, we'll use this property here to compute the difference, the distribution of the difference, X bar minus Y bar. That has a mean equal to mu X bar minus mu Y bar, mu1 minus mu2. And the standard deviation of X bar minus Y bar is the standard deviation of X bar squared plus standard deviation of Y bar squared, square root. Sigma 1 squared over N plus sigma 2 squared over N. Example, suppose we are measuring the heart rate of subjects 2 minutes after a 20-minute exercise program. There's two groups of individuals, one who performed a heavy exercise program, the other performed a light exercise program. The heart rate for those who performed the heavy exercise program 2 minutes after is 110. The mean is 110, standard deviation 7.3. For those who performed the light exercise program, the heart rate 2 minutes after is 95, standard deviation 4.5. So there's the two distributions where heart rates are coming from. These are the ones who program A was the heavy exercise program. Takes them a longer time to reduce their heart rate. There's the heart rate for the one who performed the light exercise program, that's B. Suppose we observe 15 subjects on program A, and the measurements of heart rate 2 minutes after are X1, X2 up to X15, and we do the same thing for 20 subjects on program B. Y1, Y2 up to Y20 denote these observations. What's the probability that the sample mean for program A is at least 8 units higher than sample mean for program B? So X bar, this is for program A, that has a mean with 110, standard deviation 7.3 over square root of 15. Y bar comes from a normal distribution, mu Y bar is equal to 95. Sigma Y bar is 4.5 over square root of 20. So the difference has a mean of 15. The standard deviation is the more difficult computation. Is square root sigma X bar squared, sigma Y bar squared. Sigma X bar is sigma 1 squared over N plus sigma 2 squared over M. 7.3 squared over 15 plus 4.5 squared works out to be this value here, 2.1 something. There's the distribution of the individual observations. There's the different distribution of the sample means. There's the distribution of the difference in the sample means. From that, we can compute the probability that X bar is at least 8 units higher than Y bar. That's the probability X bar minus Y bar is greater than or equal to 8. That's the probability that D is greater than or equal to 8. We know the mean of D and the standard deviation of D. So we standardize the score. We get the probability that Z is greater than minus 3.28. If you look up in the table, being less than minus 3.28 is 0.005. So being greater than minus 3.28 is 1 minus that value. So there's a 99.95% chance that X bar will be greater than 8. The sampling distribution of a difference in two proportions. So we have two success failure experiments, two populations. P1 is the probability of success for experiment 1, P2 the probability of success for experiment 2. We observe experiment 1 N1 times, and we observe experiment 2 X2 times. X1 is the number of successes for experiment 1. X2 is the number of successes for experiment 2. P1 hat and P2 hat are the proportion of successes. What's the distribution of the difference between P1 hat minus P2 hat? We know that P1 hat has a normal distribution, mu P1 hat equal to P1, sigma P1 hat equal to square root P1 1 minus P1 over N1. The same for X2. So the difference has a mean equal to mu P1 hat minus mu P2 hat, which is just P1 minus P2, and the standard deviation, square root P1 1 minus P1 over N1, P2 1 minus P2 over N2. Example, in a study by the, and a survey by the Globe and Mail, this was June 2006, there was two populations, baby boomers who were aged at that time 40 to 59. There was 664 subjects selected from this group. And then there was Generation X. Generation X are people who weren't children of the baby boomers. The children of the baby boomers called the Echo generation. Generation X were people who were not children of the baby boomers. There was 342 of those. And one of the questions they were asked, are you close to your parents? Suppose that the proportions in the population were known, and 40% of baby boomers said they were, 20% of Generation X said they were. What is the probability that this will be observed in the samples to a certain degree? What's the we'd expect the sample proportions, the difference in the sample proportions to be around 20.20. What's the probability that P1 hat minus P2 hat would be greater than or equal to 0.15? So again, we find the distribution of P1 hat. There's the mean, 0.40. There's the standard deviation. There's the same distribution for P2 hat. There's the mean, 0.20. The standard deviation, square root, 0.20, 1 minus 0.20 over 342, 0.02163. There's the distribution of the sample proportion for Generation X. For the baby boomers, we want to find the distribution of D, P1 hat minus P2 hat. The mean is equal to P1 minus P2, which is equal to 0.20. The standard deviation is a bit more complicated. It's the square root, P1 1 minus P1 over N1, P2 1 minus P2 over N2. Putting those numbers in, we get 0.0287. There's the distribution of D. It's going to be around 0.20. The probability that P1 hat minus P2 hat is greater than 0.15. That's D is greater than 0.15. Then we standardize D, subtract off its mean, divide by its standard deviation. We get probability that Z is greater than minus 1.74. Looking up in the table, minus 1.74 has an area of 0.0409 below it. So the area above it is 1 minus that. So there's a 95.91 chance that the difference between P1 hat and P2 hat will be 0.15. So, quick summary. Distribution of a sample mean. has a normal distribution. The mean is equal to the mean of the population. The standard deviation is the standard deviation of the population over the square root of n. The central limit theorem says that this is true, even if the population being sampled is not normal, if the sample size is large enough. The distribution of sample proportions. Sample proportion has a mean of equal to the population proportion. The standard deviation is the square root of p1 minus p over n. The distribution between a difference in two sample means. The mean of x bar minus y bar is mu1 minus mu2. The standard deviation of x bar minus y bar is square root sigma 1 squared over n plus sigma 2 squared over n. The distribution of a difference in two sample proportions. P1 hat minus P2 hat are the two sample proportions. The mean is equal to P1 minus P2. The standard deviation is square root P1 hat squared plus P2 hat squared, square root P1 1 minus P1 over N1 plus P2 1 minus P2 over N2. The next distribution we'll consider is the chi-squared distribution. This is the Greek letter chi. This is how the chi-squared distribution arises. Suppose you have n independent standard normal random variables. You square each one of them and add them up. That has a chi-squared distribution with mu degrees of freedom. Nu is the number of terms in the sum of squares. So quite often, statistics that are sums of squares will have a distribution related to the chi-squared distribution. There's a graph of the chi-squared distribution with mu degrees of freedom. It's a positively skewed distribution. It's totally on the positive side because when you square things and add them up, you'll get a positive number. The mean of the chi-squared distribution is the degrees of freedom. I've drawn several chi-squared distribution, one with 2 degrees of freedom, one with 3 degrees of freedom, one with 4 degrees of freedom. This arises when you square 4 standard normal random variables and add them up. This is when you have 3 standard normal random variables, square them and add them up. This is when you have 2. Statistics that have the chi-squared distribution. This statistic here is used when you're looking at the independence between two categorical variables. The data is displayed in a table. Xij is the number of cases that variable 1 is equal to I and variable 2 is equal to j. The row is equal to I and the column is equal to j. Eij is the expected frequency in the case of independence. That's, again, has a formula. It's the row total times the column total divided by n. This statistic here is a sum of squares. This can be shown to have a chi-squared distribution. The degrees of freedom is r minus 1 times z minus 1. The degrees of freedom is the number of independent terms in the sum. There's a total of r times c terms, but they're not independent. Another statistic that has chi-squared distribution. Suppose you have a sample from a normal distribution with mean mu, standard deviation sigma. You sum and square the observations minus, this should be from 1 to n. The sum is from 1 to n. the observations minus their mean. This is really, the top is really n minus 1 times s squared. The samples, if you divide at the top by n minus 1, you get the sample variance. This has a chi-squared distribution. The degrees of freedom is n minus 1. Even though there's n terms in this sum, differences of observations from the mean will add up to 0. So the last one is determined by the previous n minus 1 term. An example of using this. Suppose you had 10 observations. That's a sample size 10 coming from a normal distribution with mean 100, standard deviation 15. We'll see later on that the estimate of sigma from those 10 observations is the sample standard deviation. It should be around 15, value of sigma. What's the probability that it's between 10 and 20? This statistic, n minus 1 s squared over sigma squared, n minus 1 in this example is 10, sigma is equal to 15. This has a chi-squared distribution with n minus 1 degrees of freedom. So the probability that s is between 10 and 20, that's the same as s squared being between 10 and 400. That's the same as I'll multiply all three sides by n over 15 squared. This becomes 4. This becomes 16. The quantity in the middle has a chi-square distribution with 9 degrees of freedom. Now, you might have to use a table. You can use Excel. There's the chi-square distribution with 9 degrees of freedom. It's a skewed distribution that's centered over 9. We don't have tables to compute this area. You can use Excel functions. Excel functions will compute area. For instance, chi distribution x degrees of freedom will compute the probability that u is greater than x. It'll compute this area here. We want the area between 4 and 16. This is the area above 9. No, above 4. That's everything above 4. And I want to subtract the area above 16. That's computed from this function. It works out to be 0.84453. So today we're going to have just a short lecture and we'll stop at this point. I'll answer any questions.
Hi, Professor. There's a student in the chat saying they just joined the class and she's just wondering what to do about the tests and assignments that she's missed. Or she or he, I'm not sure.
Okay, the assignments, she can do them and hand them in. I accept all assignments, even if they're late. The tests, we will be, okay, so she would have missed 2 tests. We'll be having a total of 6 tests. I will be dropping the 2 lowest marks. Also, if she writes me an email, I can possibly give her an assignment that will give her a mark for tests 1 and 2. if she wants to, if she has a, yeah. So if she wants to write me an email, I will give her an assignment to make up for tests 1 and 2.
Okay, I'm not sure if it's a she or he, but they said they already sent you an email.
Okay, it takes me a while to read my emails,
Okay.
but I'll try to. I'll go through and if she or he sent me an email, I'll respond within the next couple of days. So the assignments that were missed, she can. I would email them to me, not submit them through the Canvas website. Okay, anyway, I'll respond to her within the next couple of days, her or him. Are there any other questions? If not, I'll end the lecture.
I have a question.
Sure.
I was wondering for the computer assignment, I could not follow the shortcuts that you did for the Excel. Do you have any PowerPoint that could show us step by step? Because
Oh, okay. What I'll do is I'll create that PowerPoint and I will send it to you. Okay.
okay, sounds good. Thank you.
Yeah. So at this point, I think I'll just.
Oh, sorry. Is there a way, if you're making a PowerPoint about this, is there a way you can post it into the Staff 245 website?
Yes, I'll post it into the Stats 245 website and put a link to it. It'll probably be in the list of lectures. Okay, I'll add it to one of the lectures there,
Okay, thank you.
the link to it. When you do the SPSS and ask it to do all of the correlations between the different events, basically what I was doing was putting that table into possibly a more useful table where I'd listed the correlations and ranged them from smallest to largest. So it was just a different way of displaying that same table. Okay, we'll stop at this point.